Hello everyone, my name is p.t.how, and I would like to tell you about our recent work on shear modulus anomaly of an unconventional superconductor. And I would like to focus the attention on the case of doped bismuth selenide. You can find our paper on arXiv. The work is done with Professor Sankit Yip from Academia Sinica, Taiwan. We did a lot more than bismuth selenide in our paper, but time is short today and I want to focus on what I consider to be the most important result. So I will start by giving a brief introduction to the nematic superconductivity of bismuth selenide. The superconducting transition of such a nematic superconductor, it is well established that it would be split into a pair of double transitions in the presence of a symmetry breaking field. And I want to talk about the shear modulus anomaly across such a pair of split transition and the implication that has on bismuth selenide. Bismuth selenide should be very familiar to many of you. As a reminder, it has a trigonal crystal structure, and that means the principal axis is threefold rotationally symmetric. We have the A and A star crystallographic direction marked. If you throw some electron donors to the mix, the material becomes superconducting as you lower the temperature. The superconductivity is interesting because very early on, people did this kind of experiments where they measure various physical quantities with an applied magnetic field parallel to the basal plane of the material, and then look at the dependence on the direction of this applied magnetic field, and they see this kind of twofold anisotropic patterns, basically for whatever they care to measure. And they only see this when you have superconductivity. And remember, the crystal symmetry is threefold, so this is incompatible with the crystal symmetry. So it is very, very tempting to then identify this as a case of nematic superconductivity, where the superconducting order parameter eta breaks both the U1 gauge symmetry and the lattice rotational symmetry at the same time spontaneously. So your eta, the order parameter, gives you a special direction. It has a direction. It behaves like a vector, basically, except that you can't tell one direction from its opposite because they are equivalent, because they differ by a negative sign, which is as good as a pi phase shift. So they are equivalent under phase transformation. But this is not the end of the story. It was realized very soon that if you take a sample, any given sample, and you repeat the same experiment, then every time you get the same twofold direction. It is persistent across multiple repeated experiments. And this cannot be explained by spontaneous symmetry breaking because, well, every time your order parameter wants to align with the red direction but not the blue directions, even though they are equivalent with respect to crystal symmetry. So somehow, something in the normal phase tells the crystal that the red direction is different from the blue ones. In other words, there has not been any rotational symmetry to begin with. It is broken already in the normal phase. If you still want to have a model of nematic superconductivity, then you can include this symmetry breaking effect naively by putting in by hand a pre-existing background, something we call a pinning field, that specifying this red direction to be special. Although I have to say that I believe there's no consensus. We are not certain what is causing this pinning effect, but we do know that it is there. Otherwise, we cannot account for what we see in the experiment. So this is our motivation. This is where we come from. You see, at first, you say that there is rotational symmetry breaking at the superconducting transition. Therefore, we need nematic superconductivity to account for that. But then later you come back to me and tell me that there's no rotational symmetry to begin with, much less the breaking of it. So now what? So we want to propose experimental tests that can be carried out by our experimentalist colleagues that test for nematic superconductivity that can distinguish between the nematic scenario and possibly, I don't know, anisotropic S-wave, so that even without referring to the rotational symmetry, even when there's no rotational symmetry to begin with. And we argue that the split transitions of a nematic superconductor would be a good experimental signature to test for in this regard. But first of all, I want to establish a model for nematic superconductivity without a pinning field. So let's forget about the pinning field for now. Let's assume that the crystal symmetry is still intact, only waiting to be broken spontaneously by the vector order parameter eta. So can we write down the Ginzburg-Landau theory for eta in a trigonal crystal? Remember, it's like writing down the power series expansion for your free energy, and you have to require that every term that enters your free energy to be invariant under any crystal symmetry transformation. If you go through the mathematics with the trigonal lattice group for Bismuth selenide, you'll find out that if you do the expansion up to 6th order in eta, then the most general free energy expansion that you can come up with favors eta to align with some kind of high symmetry lattice direction, the A star direction as plotted here. And we put back the pinning field on top of that, and assuming the pinning field is in the A direction. You can always have that experimentally. For any given piece of sample, the pinning field is either in A or A star direction. We don't know why, because we don't know for certain what's causing this pinning field, but we do know that this seems to be the case. So the implication is that you make a bunch of these samples, you test for the twofold direction in each of them, and presumably half of the sample would have their pinning field in the A direction. So for Bismuth selenide, you really get this set up for free. With a pinning field in place, when the sample first turns superconducting across this so-called upper transition, the order parameter grows and aligns itself with a pinning field in the A direction. As the temperature is lowered, the order parameter grows in magnitude, but the orientation is locked along the A direction because this is still a high symmetry direction. It is symmetry protected. Until you get to the point where the order parameter is large enough so that the 6th order term in the free energy expansion becomes competitive with a pinning field effect. Remember, the 6th order term wants the order parameter to align with the A star direction instead. So the competition drives a spontaneous symmetry breaking, a 2nd order transition here, the lower transition, where this remaining twofold symmetry is broken and the order parameter can choose to rotate either clockwise or counterclockwise toward the nearest A star direction. The observation of this lower transition would be a very, very decisive evidence for the nematic superconductivity, except it has never been seen. And we argue that shear modulus anomaly would be a good thing to look for if you are trying to hunt down this split pair of transitions. I should say that if you have a single component order parameter like an S-wave case, then by symmetry it cannot even couple with a shear strain. So if you see anything funny happening in the shear sector across a superconducting transition, then that would be enough proof that you have a multi-component order parameter, you have nematic superconductivity. But anyway, let's look at what happened to the shear modulus at the upper transition. Remember, the upper transition is about the order parameter start to grow in the A direction. So if you consider these two different shear modes, the one on the left can couple to the order parameter, to this order parameter by symmetry, but the one on the right doesn't care about that, doesn't couple to that. Intuitively, this is the picture, and indeed, this is what happened if you go through the mathematics. You write down the Ginzburg-Landau theory, you couple the shear strain to the superconducting sector, and you find out that in this channel, the shear modulus has a step discontinuity at the upper transition, and nothing happens there. This is already a non-trivial signature that you can look for in an experiment. It gets even more interesting at the lower transition. The lower transition is about the spontaneous breaking of this remaining twofold symmetry, where the order parameter can go either clockwise or counterclockwise. So at the point of the transition, the system is ready to go one way or the other. If you just give it any infinitesimal perturbation, it is ready to give you a large response. So imagine if you try to apply a shear stress in this channel, the system will give you a very large distortion with an infinitesimal stress applied. In other words, this is a soft mode. Or let me say this again. We predict that the shear modulus C66 that corresponds to this channel vanishes at the lower transition. If you consider the temperature dependence, you see that the C66 comes in at some finite value, it drops all the way to 0 at the lower transition, and then it goes up again when you enter the lower phase. This is not a kink, this is not a step discontinuity, this is a 0. It's very dramatic, and I believe that if you are trying to look for this kind of signature, it's very difficult to miss it. In conclusion, we hope that the experimentalist can go and look for this split pair of transitions in bismuth selenide, so to prove or disprove convincingly that it is a nematic superconductor. Our theoretical predictions that at the lower transition, the shear modulus C66 has to vanish, goes all the way down to 0. And this should be a very, very dramatic signal that if you are trying to look for it in, say, an ultrasound experiment, it should be very difficult to miss. Thank you for your attention.